morning, class. Today we're going to be talking about nonlinear differential equations, and in specific the Bernoulli equation. So how do we solve a first order nonlinear equation? Well, some of those equations can be turned into linear equations and solved that way using the regular linear solving method. So one of those is the Bernoulli equation, which has the form y prime plus some function of x times y is equal to some function of x times y to some power. That power is not equal to 0 or 1 because otherwise that would just be a linear ordinary differential equation, and we know how to solve those. So in order to be able to linearize this equation, we're going to define a dependent variable u, and that variable u is going to be equal to y to the 1 minus whatever n is. So then we have y is equal to u to the 1 over 1 minus n, and y prime is equal to 1 over 1 minus n times u to the n over 1 minus n times u prime, whatever that is. So in order to linearize the equation, we're going to substitute equation 2 into equation 1 up here and get this form. And dividing by this front part in front of the u prime, we have a u prime times 1 minus n times p of x times u equals 1 minus n times q of x, which is now an ordinary differential equation, and it can be solved using the general linear solution. So let's take a look at a quick example of what this might look like. So let's solve an equation y prime plus y is equal to y squared. This is one of the most easiest cases. P of x is equal to 1, q of x is equal to 1, and n is equal to 2. So we're going to first turn it into a linear ordinary differential equation. U is y to the negative 1, so then y is equal to u to the negative 1. Y prime is negative u to the negative 2 times u prime. And as above, we plug equation 2 into our given differential equation to get negative u to the negative 2 times u prime plus u to the negative 1 is equal to u to the negative 2. So then, multiplying by this term in front of the u prime, we get u prime minus u is equal to negative 1. Seems fairly easy to solve, so we're going to solve this using the general solution for the linear differential equations, which we can start by finding the integrating factor, which is e to the integral of the p of x function. For us, that's 1 here, so then we end up with e to the negative x, and you can see that I chose to integrate from 0 to negative x instead of x, because this will make some things in the future easier to simplify. And also we chose a to be 0 in this case because we want f of a equals 0 when we choose a. So let's multiply equation 4 by equation 5, which is our integrating factor, and we get this equation right here. And now we have a ordinary differential equation which we can solve. So if we notice here, this left side of the equation can be simplified using the product rule of calculus. So then we end up with this equation, and the right side stays the same. We integrate over x. This makes the derivative and the integral go away here, and the integral of negative e to the negative x dx is just e to the negative x plus some constant, and then dividing by e to the negative x, we have a solution for u, which is 1 plus some constants times e to the x. And now that we have u, when we solved it using the linear equation that we defined in u, we can now find y based off of u. So our y that we defined at the very beginning, right here, our y that we defined right here with respect to u is now equal to 1 over 1 plus some constant times e to the x. And of course, if you have boundary conditions, then you can solve for that constant. And that is all. Thank you all for coming to my lecture, and have a good day.